We know that a current produces magnetic field around itself. But what would happen if we place a current carrying wire in a magnetic field? A current carrying wire which behaves like a magnet, if placed in a magnetic field, yes, of course, it will experience a force. The direction of the force acting on a current carrying wire placed in a magnetic field is given by Fleming's left-hand rule. To implement Fleming's left-hand rule, stretch your thumb, index finger and the middle finger 90 degrees to each other as shown by the model. The middle finger points in the direction of current. The index finger points in the direction of magnetic field. The thumb then will point to the direction of force acting on the wire. Let us utilize Fleming's left-hand rule in our case to find out the direction of force on this current carrying wire. The direction of current is shown by the middle finger. The direction of magnetic field is from north to south, hence the index finger should point from north to south. Now the thumb is showing us the direction of force, which is downwards. Now let's see what would happen if you place a current carrying coil in a magnetic field. Consider this current carrying coil placed in a magnetic field. The direction of current is as shown. Let us use the Fleming's left-hand rule to see the forces acting on each of the arm of the coil. The left arm has current moving upwards. The direction of magnetic field is from north to south. Hence, the force acting on the left coil is outside. Similarly, for the right coil, the current acting is downwards. The magnetic field is from north to south, hence the force is acting inside. This creates a turning effect on the coil. But the coil will stop in half turn. If it tries to move beyond that point, the force acting on the left arm is outwards, which will push it back and it will not be able to move any further. But what if we want to have continuous rotation? What kind of device can help us achieve that? In order to achieve continuous rotation, we use a device called the split ring commutator. It is, as the name suggests, a ring which has been split into half. This ring is attached in such a manner that when the coil spins, the ring spins with it. Here we see a current carrying coil attached to a split ring commutator. There are magnets to provide magnetic field. These are carbon brushes which provide electrical contact to the split ring commutator. They are called brushes because they are not fixed with the commutator but just touching so that the commutator can move freely. Let us imagine the current flowing in the left arm. The direction of current is from positive to negative, and hence the direction of current will be as shown. If we use Fleming's left hand rule, the force on the left arm will be outside, which will cause a turning effect on the coil, and hence the coil will begin to turn. As the coil turns, so does the split ring. You would notice that the red ring, which was touching the positive terminal of the battery, after half turn is now touching the negative terminal, which reverses the direction of current in that arm, and hence also reverses the direction of force acting on it. So if the force before was acting outside, now will start acting inside, and hence the coil will continue to rotate. This is the working of a simple motor. How to increase the strength of the motor? By increasing the current, increasing the number of turns on the coil, increasing the strength of the magnets.